In the unending, silent theatre of the cosmos, there are phenomena so extreme they defy our most fundamental intuitions about reality. They are the universe's ultimate expressions of gravity, ghostly presences that bend light, devour stars, and warp the very fabric of existence. We call them black holes. For decades, we saw them as cosmic vandals, points of no return, celestial prisons from which not even light, the fastest thing in the universe, could escape. But a new understanding is dawning. This perception is shifting from one of pure destruction to one of profound revelation. These enigmatic objects, these tears in the continuity of space-time, might not be endings at all. They could be the most important clues we have, cosmic laboratories where the deepest secrets of space and time are forged and held captive. The quest to comprehend these gravitational titans is more than an astronomical curiosity. It is a journey to the absolute limits of human knowledge, a confrontation with the two pillars of modern physics, and a search for the source code of the universe itself. Our story begins not in the cold vacuum of space, but in the fertile ground of the human mind, long before we had the tools to peer into the galactic darkness. The concept of an object so massive that its gravity could trap light was not born from the complex mathematics of the 20th century, but from the brilliant intuition of an 18th century English clergyman named John Michell. In 1783, working by candlelight and with Newton's laws of gravity as his guide, Michell engaged in a thought experiment of breathtaking prescience. He understood the concept of escape velocity, the speed an object needs to break free from a celestial body's gravitational pull. A cannonball fired from Earth must reach a colossal speed to escape into space. Michell reasoned that a more massive body would require an even greater escape velocity. He then asked a question of startling simplicity and revolutionary consequence. What if a star was so massive, so incredibly dense, that its escape velocity exceeded the speed of light itself? Using the best contemporary measurements for light's velocity, he calculated that a star with 500 times the diameter of our Sun, yet with the same density, would possess such an overwhelming gravitational field. Light particles, or corpuscles as Newton had imagined them, would be pulled back to the surface, unable to break free. The star would become invisible, a dark star shrouded in an eternal, self-imposed night. This was a staggering intellectual leap, predicting a cosmic monster from nothing more than pure reason and classical mechanics. A decade later, the renowned French mathematician Pierre-Simon Laplace, unaware of Michell's work, independently arrived at the very same conclusion. Yet, this revolutionary idea, born in the Age of Enlightenment, soon faded into obscurity. The scientific consensus shifted. Light was re-envisioned not as a particle, but as a wave, and it was unclear how a wave could be trapped by gravity. The notion of dark stars was dismissed as a curious relic of a superseded theory, a footnote in the history of astronomy, and for more than a century, the universe remained a well-lit, predictable, clockwork machine. It would take the arrival of a true titan, a man who would not just amend our understanding of gravity, but completely shatter it, to resurrect this forgotten concept from its intellectual grave. Albert Einstein did not set out to find cosmic monsters. He was wrestling with a deeper problem, a fundamental conflict between Newton's theory of gravity, which described an instantaneous force acting across distance, and his own newly minted theory of special relativity, which decreed that nothing, not even the influence of gravity, could travel faster than the speed of light. His decade-long intellectual struggle culminated in 1915 with his general theory of relativity, a masterpiece of human thought that presented a radically new vision of the cosmos. In Einstein's universe, gravity was not a force pulling objects together. Instead, it was a consequence of the curvature of a unified, four-dimensional fabric, space-time. To truly grasp this concept, we must abandon our everyday intuition. Imagine space-time as a vast, taut, cosmic trampoline stretching to infinity. A planet, like a small marble, placed on this trampoline would create a tiny dimple. A star, like a heavy bowling ball, would create a much deeper depression. According to Einstein, planets do not orbit the Sun because of a mysterious pull. They are simply following the straightest possible path through the curved space-time created by the Sun's mass. They are rolling around the edge of the deep well carved by the star. This elegant and beautiful theory explained anomalies in Mercury's orbit that had puzzled astronomers for centuries and made astonishing predictions, like the bending of starlight by the Sun's gravity, which was famously confirmed during a solar eclipse in 1919. But hidden within the dense mathematics of Einstein's field equations was something far stranger, something that even Einstein himself found deeply unsettling. The revelation came from an unlikely source. In the midst of the carnage of the First World War, a German physicist named Karl Schwarzschild was serving on the Russian front, calculating artillery trajectories. In the brief lulls between battles, he turned his powerful mind to Einstein's new theory. Incredibly, while surrounded by the chaos of war, Schwarzschild found the first exact solution to the equations of general relativity describing the space-time geometry around a single, spherical, non-rotating mass. His solution confirmed Einstein's predictions for bodies like our Sunday, but it also contained a mathematical bombshell. Schwarzschild's equations showed that if you could compress enough mass into a small enough volume, the curvature of space-time would become infinite. The fabric of reality would be punctured, creating a point of zero volume and infinite density, a singularity. Surrounding this singularity was a boundary, a one-way membrane in space-time. At a specific distance from the central point, now known as the Schwarzschild radius, the gravitational pull would become so immense that the escape velocity would equal the speed of light. Beyond this boundary, nothing could ever get out. Schwarzschild had mathematically resurrected Michel's dark star, but in a form far more bizarre and terrifying than anyone had ever imagined. Einstein was disturbed by this implication, believing that nature would somehow prevent such singularities from forming. He thought they were a mere mathematical anomaly, a flaw in the theory that would eventually be resolved. He was wrong. The universe, it turned out, was perfectly capable of creating these monsters. To journey toward one of these objects is to journey to the edge of reality itself. From a great distance, a black hole is deceptively simple. It is a sphere of perfect blackness, a hole in the starry tapestry of the cosmos. But as we approach, the universe begins to contort in profoundly strange ways. The light from distant stars behind the black hole is bent around its edges, an effect called gravitational lensing, creating a halo of distorted, duplicated images. The most crucial feature is the event horizon, the modern name for Schwarzschild's boundary. It is not a physical surface you could touch. It is a demarcation point in space-time itself, a threshold of no return. Imagine a powerful, wide river flowing towards a colossal waterfall. Far upstream, the water moves slowly. A boat with a strong engine can easily navigate, even turning around and heading back upstream. As the boat drifts closer to the falls, the current quickens. The engine must work harder to fight the flow. Eventually, the boat reaches a point where the water is flowing so fast, faster than the boat's maximum speed, that escape becomes impossible. No matter how hard the engine works, the current will inexorably pull it over the edge. The event horizon of a black hole is precisely this point of no return for light itself. At this boundary, space-time is flowing inward at the speed of light. Since nothing can travel faster than light, anything that crosses the event horizon, a spaceship, a planet, a beam of light, is trapped forever, destined to continue its one-way journey to the central singularity. For an observer watching from a safe distance, something even stranger occurs. As an object falls toward the event horizon, time for that object appears to slow down. This is time dilation, a core prediction of relativity. The light from the falling object becomes stretched, its wavelength increasing, shifting toward the red end of the spectrum. The object would appear to move slower and slower, growing redder and dimmer, until it seems to freeze at the edge of the horizon, suspended for eternity, eventually fading from view as its light is redshifted into oblivion. The falling object, however, would experience no such pause. From its perspective, it would cross the event horizon in a finite amount of time, unaware of the exact moment of passage. Once inside, its fate is sealed. The gravitational forces are so extreme that they would stretch any object vertically while compressing it horizontally, a gruesome process dubbed spaghettification. But the final destination is the singularity. Here, all the mass of the black hole is crushed into an infinitesimally small point. Here, the curvature of space-time becomes infinite. And here, our laws of physics, including Einstein's own theory of general relativity, break down completely. The singularity is not a place in the universe. It is a moment in time, an end of time itself. It is a declaration from the cosmos that our current understanding is incomplete. For much of the 20th century, black holes were considered theoretical curiosities, mathematical oddities too extreme to exist in reality. But as our understanding of stellar evolution grew, we realized the universe was a prolific black hole factory. When a star at least 3 times more massive than our Sun exhausts its nuclear fuel, it can no longer support its own weight against the crushing force of gravity. The core collapses catastrophically, triggering a spectacular supernova explosion that blasts the star's outer layers into space. What remains of the core continues to collapse inward, unchecked, until it is crushed past its own Schwarzschild radius, forming a stellar mass black hole. Our galaxy is likely littered with tens of millions of these stellar corpses silently drifting through the void. Yet, these are the minnows of the black hole world. At the heart of nearly every large galaxy, including our own Milky Way, lurks a supermassive black hole, a behemoth weighing millions or even billions of times the mass of our Sunday. The one at our galaxy's center, Sagittarius A star, is 4 million solar masses. The giant at the core of the galaxy, M87, the first ever to be imaged, is over 6.5 billion solar masses. How these monsters formed is one of the great puzzles of modern cosmology, but their gravitational influence orchestrates the dance of stars in the galactic core. There might even be a third, more elusive type, primordial black holes, hypothesized to have formed in the chaotic, ultra-dense conditions of the very first second after the Big Bang. If they exist, these microscopic black holes could be drifting through the cosmos right now, and some scientists even speculate they could be the mysterious dark matter that constitutes most of the mass in the universe. For a long time, the classical picture of a black hole was absolute. It was a perfect prison. What goes in never comes out. They were viewed as cosmic dead ends, information destroyers that would grow in mass but never shrink. This simple, elegant picture was profoundly challenged in the 1970s by the brilliant mind of Stephen Hawking. Hawking began to investigate what would happen if one brought the strange rules of the other great pillar of modern physics, quantum mechanics, to the edge of a black hole. Quantum mechanics governs the universe of the very small. It is a world of probabilities, uncertainty, and bizarre phenomena. One of its strangest predictions is that so-called empty space is not empty at all. The vacuum is a seething cauldron of activity, a quantum foam where pairs of virtual particles, a particle and its antiparticle, are constantly popping into existence, briefly separating and then coming back together to annihilate each other in a flash of energy. This happens on timescales so short they are almost unimaginable. Hawking had a revolutionary insight when he applied this concept to the event horizon. Imagine a pair of these virtual particles spontaneously appearing right at the edge of a black hole. Ordinarily, they would quickly annihilate. But what if one particle appears just inside the event horizon, while its partner appears just outside? The inward falling particle is immediately captured by the black hole, while the outward moving particle is now free to escape into space. It can no longer annihilate with its partner. To a distant observer, it would look as though the black hole itself is emitting a particle. This process, now known as Hawking radiation, has a profound consequence. In the quantum world, energy must be conserved. The escaping particle has positive energy, which it carries away from the black hole. To balance the cosmic books, the particle that fell into the black hole must be considered to have negative energy. This negative energy is subtracted from the black hole's total mass. The result is astonishing. Black holes are not truly black. They glow with a faint thermal radiation, and in doing so, they slowly, incredibly slowly, lose mass. They evaporate. The process is excruciatingly slow for large black holes. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate, a timescale vastly longer than the current age of the universe. But the implication is earth-shattering. Black holes are not eternal. They will eventually radiate away their entire mass and disappear in a final puff of radiation. This stunning discovery created one of the deepest paradoxes in the history of science, the black hole information paradox. A central tenet of quantum mechanics is that information can never be truly destroyed. Information, in this context, refers to the precise quantum properties of every particle that has ever existed: its position, momentum, spin. If you know the complete quantum state of a system now, the laws of physics say you should be able to calculate its state at any point in the past or future. Information is always conserved. But what happens when a particle, with all its unique information, falls into a black hole? According to Hawking's initial calculations, the black hole eventually evaporates, but the radiation it emits is thermal and random. It appears to contain no information about what fell in. The outgoing radiation from a black hole formed from a collapsed star would be identical to the radiation from a black hole formed from a collapsed library of encyclopedias. So where did the information go? Did it vanish from the universe, violating a fundamental law of quantum physics? Or is it somehow encoded in the outgoing radiation in a way we don't yet understand? This question ignited a decades-long debate among the world's leading physicists. Hawking himself initially argued that the information was lost forever, a claim that sent shockwaves through the theoretical physics community. If information could be destroyed, our most basic understanding of reality would crumble. It suggests that the past can be completely erased, that the universe has no fundamental memory. The search for a solution to this paradox has driven some of the most profound theoretical developments of the last half-century, forcing us to question the very nature of space-time itself. And it is this pressure, this conflict between relativity and quantum mechanics at the edge of the black hole, that is forcing us to peer inside, into the true heart of the mystery. What happens to space and time once you cross the event horizon? According to the mathematics of general relativity, something truly mind-bending occurs. The roles of space and time essentially interchange. In our everyday experience, we are free to move in any direction in the 3 dimensions of space: forward, backward, left, right, up, down. But we are inexorably propelled forward in one dimension, time. We cannot stop moving into the future. Inside the event horizon, this is flipped. The spatial dimension pointing toward the singularity becomes the new, time-like direction. All possible paths, all future trajectories for any object, bend inward toward the singularity. Trying to move away from the singularity once inside the event horizon is as futile as trying to stop yourself from moving into next Tuesday. The singularity is no longer a place in space. It is a moment in the future, an inevitable end for anything that crosses the boundary. Conversely, the time dimension becomes space-like, meaning it might, in theory, be possible to move through it. This bizarre swapping of the fundamental coordinates of reality is a direct consequence of the extreme warping of space-time. It tells us that a black hole is not just a place where gravity is strong, it is a place where the fundamental structure of reality is transformed. This profound connection between gravity, information, and the boundaries of space-time has given rise to one of the most speculative and tantalizing ideas in all of science, the holographic principle. First proposed by Gerard Hooft and later refined by Leonard Susskind, this principle emerged directly from the struggle with the black hole information paradox. It suggests that all the information needed to describe a 3-dimensional volume of space can be completely encoded on a 2-dimensional surface that surrounds it, much like a two-dimensional holographic film can encode all the information for a three-dimensional image. Black holes are the perfect test case for this idea. The information paradox arises because information seems to disappear into the 3D volume of the black hole. The holographic principle suggests that the information never truly enters the volume. Instead, it gets stuck or imprinted on the 2D surface of the event horizon itself. When the black hole evaporates via Hawking radiation, that information is then slowly and subtly released back into the universe, perfectly preserved. If this is true for a black hole, could it be true for the entire universe? Could our three-dimensional reality, with all its richness and complexity, be nothing more than a holographic projection of information stored on a distant, two-dimensional boundary at the edge of the cosmos? This is a radical, almost philosophical conjecture, but it is a mathematically robust idea that could potentially unite general relativity and quantum mechanics. It suggests that space itself is an emergent property, a construct built from more fundamental quantum information. The black hole, in this view, is our most powerful magnifying glass, showing us the pixelated, informational nature of space-time at its most fundamental level. The mathematical labyrinth of black hole physics also hints at even more exotic possibilities. The original solution found by Schwarzschild describes an idealized, eternal black hole. When extended, this mathematical framework also describes its theoretical opposite, a white hole, a region of space-time from which matter and energy can only escape but never enter. It is a time-reversed black hole, a cosmic fountain spewing out matter and energy. Furthermore, the theory allows for the connection of these two objects, forming an Einstein-Rosen bridge, more famously known as a wormhole, a potential shortcut through space-time. While most physicists believe that such wormholes would be incredibly unstable and impossible to traverse, their existence as a valid mathematical solution to Einstein's equations remains a tantalizing possibility. It hints that the singularity at the heart of a black hole might not be an end, but perhaps a gateway to another region of space-time, or even another universe entirely. These ideas remain firmly in the realm of speculation, but they underscore how black holes push our imagination to its absolute limits, forcing us to contemplate a cosmos far stranger than we can observe. For decades, this entire discussion was purely theoretical. Black holes were creatures of pen and paper, but the evidence for their physical existence has become undeniable. We cannot see them directly, but we can witness their profound gravitational influence on their surroundings. We see stars at the center of our galaxy whipping around an unseen, compact object at incredible speeds, their orbits betraying the presence of the supermassive black hole Sagittarius A star. We observe matter being siphoned from a companion star, forming a superheated, glowing accretion disk as it spirals toward a black hole's event horizon, blazing with X-rays before it disappears. In distant galaxies, we see quasars, accretion disks around supermassive black holes that outshine their entire host galaxy. But the most direct and revolutionary evidence arrived in 2015, not as light, but as a vibration in space-time itself. The Laser Interferometer Gravitational Wave Observatory, or LIGO, detected the faint ripples of gravitational waves for the very first time. These waves were the echo of a cataclysmic event that occurred over 1 billion years ago, the collision and merger of two stellar mass black holes. As they spiraled into each other, they churned the fabric of space-time, sending out waves of gravitational energy that finally washed over Earth. That faint chirp, lasting only a fraction of a second, opened an entirely new window onto the universe. We could finally listen to the dark, silent cosmos. Then, in 2019, humanity achieved another monumental feat. The Event Horizon Telescope, a global network of radio telescopes synchronized to act as a single, Earth-sized observatory, captured the first ever direct image of a black hole's silhouette. They pointed this planetary lens at M87, a giant galaxy 55 million light-years away. After years of observation and data processing, the image was revealed, a bright, glowing ring of superheated gas surrounding a perfect circle of darkness. We were looking at the shadow cast by the event horizon itself, a direct visual confirmation of Einstein's predictions on a scale almost too vast to comprehend. We had seen the unseeable, we had photographed the abyss. We stand now at a remarkable precipice in our cosmic journey. The black hole has transformed from a mathematical curiosity into a tangible, observable object. It is the ultimate crucible, the one place in the universe where our two great theories, general relativity and quantum mechanics, must meet and be reconciled. Solving the information paradox may lead us to a final, unified theory of quantum gravity, the holy grail of modern physics. Understanding the nature of the singularity could reveal what happened before the Big Bang, or even show us that our universe is just one among many in a vast multiverse. The secrets locked within these gravitational prisons are not just about the objects themselves, they are about the fundamental nature of information, the origin of space, and the ultimate fate of time. They are the gatekeepers to a deeper understanding of reality. They represent a boundary, not just in space-time, but for human knowledge. And like all great explorers before us, we are drawn to that boundary, compelled by an insatiable need to see what lies beyond. The black hole does not just hold the secret to space and time, it holds a mirror up to our own quest for meaning, reflecting our deepest desire to understand our place in this vast, mysterious, and magnificent cosmos. The key is there, locked in the darkness, and our search has only just begun.